Equivalence of cardinality in musical analysis occurs extremely frequently. In order to develop musical texture, pitches are often repeated, either in the same voice or by a different instrument, so it is useful in analysis to be able to relate these sets based solely on their unique pitch content, rather than looking at every single pitch attack. It is important to remember that as long as p-equivalence is not applied, all sets are ordered. Therefore, when dealing with the equivalence of cardinality of sets, the order of the first instance of each element must remain the same, unless of course p-equivalence is applied. The cardinality equivalence relates sets whose ordered subsets of unique elements are equal. This definition of cardinality varies from the manner in which the term is normally used, in that these sets are assumed to be ordered. In analysis, this equivalency will generally be used in conjunction with p-equivalence. As an example of this equivalence, we will look at these two sets. The ordered subsets of unique elements for both sets would be C4, E4, G4. This represents a slight variation from the definition of the original article. The original definition would only allow for mapping of adjacent repeated elements, but this definition was expanded to include non-adjacent elements in order to make it more versatile. Because both sets have the same ordered subsets of unique elements, the two sets are equal under C equivalence and would be identified by the set C4, E4, G4 in three-dimensional space. The model of this equivalence is much different than the previous models. Before, we relied on the fact that we had fixed dimensionality, which is based on the cardinality of sets, but with cardinality equivalence we no longer have that luxury. We are now dealing with sets that have variable number of elements and therefore models with variable number of dimensions. Ultimately, we would need to create a model with an infinite number of spaces embedded within each other, but realistically we will only deal with a few of these levels. When building this model, it is easiest to start with the lower dimensions and build our way up. Because a set with only one element in it cannot contain repeated elements, we will start with sets containing exactly two elements. In a two-dimensional space, the set of points with repeated values, that is, x, y, where x equals y, lies along the line y equals x, for instance 1, 1. This point under C equivalence is mapped to the single-dimensional space at point 1. It no longer exists in two-dimensional space, but rather in the one-dimensional space that is embedded within the two-dimensional space. In a three-dimensional space, there exists three embedded two-dimensional planes. Imagine a stack of two-dimensional planes. At the center of that stack is the zero plane, designated by the third element of the set, x, y, z, where z equals 0. If we assume that also x equals 0, and y can equal anything, that is, the y-axis, that line is part of the two-dimensional space embedded within the three-dimensional level of C space. Therefore, the first two-dimensional space relative to three dimensions is the plane x, y, z, where x equals z, and where y equals anything. The second is very similar, where y equals z, and x equals anything. The last requires that y equal x, a line that we are very familiar with, and z can equal anything. The intersection of these planes is where x equals y equals z, which is the single-dimensional space embedded within C space. Modeling four dimensions presents issues because the fourth dimension, that is time, is not a spatial dimension like the first three, but we can describe it as a three-dimensional space embedded within four dimensions. Because all of these models were limited to two dimensions, the line y equals x will be the only embedded subspace. In O space, this is the line that wrapped around the torus in both directions, and is the same in OP and OI space. In P space and I space, this is the boundary of the plane. Because T space maps two dimensions onto a single dimension, the embedded subspace is the point 0, that is a unison. OT and OPT spaces are a circle, similar to a clock, with the point 0 being the subspace. OTI, OPTI are similar to OT, but with a half circle. Despite the complexities of the infinite number of spaces embedded within each other, cardinality equivalence is an extremely valuable tool that lets us equate different musical textures and realizations rather than having to deal with repeated notes as individual events. Ultimately, these models do not provide a practical tool for analysis. However, they provide an invaluable means for conceptualizing these complex spaces and the mathematics behind them. When looking at static node models, it is easy to forget that these spaces are actually composed of continuous pitches. Additionally, the use of video shows the motion between spaces, which would have never been possible to achieve in print. Modeling one space moving to another not only aids in the conceptualization of the spaces themselves, but provides deep insight into the way we analyze music and the implications of these relationships that are often assumed to exist without question.